Good afternoon, dear colleagues, and today we continue our medical decision support systems course, and we are talking about artificial intelligence, and this part of our course is related to uh, concepts of machine learning and previously, we covered basic algorithms in machine learning, and we'll continue with the next step with deep learning and neural networks. And this area is the most promising one in digital technologies in healthcare and in general in digital technologies. And deep learning and neural networks are very important. There are a lot of different types of neural network and different types of applications built on neural network. And we will try to make an overview of general neural network concepts. In the future, we will talk about machine learning and particular about uh, neural networks and why it's so important. And neural network is an attempt to reproduce the functioning of the human brain using mathematical models. Artificial neuron or mathematical neuron is a formal concept for to realize a non-artificial neural network in digital form. And it's simplified model of natural constructs. Mathematically, an artificial neuron is usually represented as some non-linear function on a single argument, a linear combination on all output signals. This function is called activation function, and this function is a transfer of the signal from one neuron to another. The resulting is sent to the output layer of this neural network. Such artificial neurons are combined into networks. They connect the outputs of some neurons to the input of others. Artificial neurons and networks are the main elements of an ideal neural computer. Artificial neural circuit is a concept of processing output, process creating output signals. It arrive as a based on the input of the given signal added to the transfer function or calculation function, which will be based on the weights in this neuron. Neurons are generally classified based on their position in the network topology. We can find input neurons which receive the original vector encoded the input signal. Typically, these neurons do not perform computational operations, but they simply pass the received input signal to the output, possibly amplifying or attenuating it. Output neurons represent the network output data. Any computational operations can be performed in the output neurons. Intermediate neurons perform basic computing operations. Neurons in neural networks are essentially miniature logistic regression models. A neural network layer consists of a set of neurons, each receiving the same input. Fully connected layers, also called dense layers is a set of neurons that receive the same input data. These neurons perform a linear combination of inputs and the layer parameters produce an output. This output can then be passed to another layer. The architecture or topology of a neural network is how these layers are organized. Activation function. What does an artificial neuron do? It, uh, in simple terms, it calculates the weighted sum from its inputs, added and offset, and decides whether this value should be excluded or continued. The activation function, in fact, serves exactly in this role. Exactly, the activation function determines the output value of the neuron depending on the result of the weighted sum of the inputs and the threshold value. Thus, the activation function was one of the most powerful tools that influences the magic attributed to neural networks. In part, it determines which neurons will be activated. In other words, and what information will be transmitted to subsequent layers. Let's consider a neuron having inputs receiving values at the inputs with weight coefficient with 0. As we can see, the weighted sum can take any value in the range from uh, minus infinity to plus infinity. Now let's think, how do we decide whether a neuron should be engaged or activated? Indeed, the neuron doesn't know the boundary after which its activation should follow. It's for the purpose that the value obtained by the adder is transferred to the activation function. It checks the weighted sums as to whether external connections should consider this neuron is activated or whether it can be ignored. Step activation is another algorithm which could be used here. And this activation function is very simple, and there are only two values in it, 0 or 1. So this neuron could be activated or not. If we remember that we have a constant bias, we can use it to move the activation point to the function to 0, which will give us another entry. Otherwise, our first activation function takes a value when exceeds the limit value, and the value is 0, so it's not activated. This is a very simple method, but it has significant drawbacks. If our task is to implement binary classifier, that is a model that needs to say yes or no, activated or not. The step function will do it for us since it does exactly that. Now let's make this task more complicated. Imagine that we need a large number of neurons for classification of several mutually exclusive classes. Class 1, class 2, class 3, and so on. What do we do if more than one neuron is activated? All activated neurons with a step function will give a value of 1. And we will get a logical question on which class should we classify the object being tested. If we want only one neuron to be activated and the activation function of of the other neurons to be zero, since only in this case can we be sure that the network correctly determines the class. Then such a network is more difficult to train and achieve uh, convergence. The output in a non-binary activation function, that is, the possible values are activated by 50%, activated by 20%, and so on. Then in the case of activation of several neurons, it's possible to find the neuron with the highest value of the activation function. Of course, in this case, as before, there will still be a problem if more than one neuron is said to be 100% activated. However, the existence of intermediate values in the output of a neuron will make the training process smoother and faster, and the likelihood of having several fully activated neurons during training is significantly reduced compared to a stepwise activation function. And through this dependence on what are you training and on what data. So we realize that we are not interested in binary yes and no in activation functions, but in intermediate values of the activation process. In this case, the first thing we will look at is linear function. A linear function is a straight line and is proportional to the input. That is the weight sum of the neuron. This choice of activation function allows us to obtain a spectrum of values and not just a binary response. It's possible to connect several neurons together and it more than one neuron, and if more than one neuron is activated, we'll get our results. It turns out that we will not. Firstly, some learning methods, gradient descent, backpropagation, will not work correctly for us. But the main problem is different. Let's look at the connected layers. We activate each layer with a linear function. The value from the function goes to the next layer as input. The second layer also makes a weighted sum of the input of its input and in turn fires neurons depending on another linear activation function. As a result, regardless of the number of layers that are linear in nature, the final activation function in the last layer will simply be a linear function of the inputs in the first layer. So we don't need these internal layers in this case. Stop for a moment and consider this thought. That's two layers, or there are n layers, are represented by one. That's we lost the ability to make sets from layers. It doesn't matter how we put the layers together, all we receive now from this network will be similar to one layer with a linear activation function. Since linear combination of linear functions is another linear function. Let's move on to more complex examples of activation functions. All of them are non-linear by their background. The non-linearity of these functions is responsible for increasing the degree of freedom, allowing high-dimensional problems to be generalized to lower dimensions. Here are examples of common activation functions. Sigmoid. Sigmoids looks smoother and similar to a step function. Let's consider its advantages. Firstly, sigmoid is not binary. That's we get analog activation as opposed to the step function. For sigmoid, smooth gradient is also a characteristic. This function on linear nature that is a linear combination of such functions produces a non-linear function as a result. This means we will be able to collect, or as it's used to say, stack layers in different neurons. Another advantage here is in using sigmoid over a linear function is sigmoid is always fixed in a range between 0 and 1, while a linear function varies in minus infinity and infinity. This property is sigmoid is very useful because it eliminates overflow errors, and in the case of large activation values they will be uh, not a problem. Sigmoid is very popular as activation function in neural networks, but it's not without some drawbacks. As you can see, when approaching the end, sigmoid function values react poorly to changes in the input value. Consequently, the gradient in such areas takes on small values. This in turn leads to problems with the extinction gradient. What does this mean? The gradient value is small or vanishingly small. It doesn't receive any computable changes. As a result, the neural network doesn't train further or doesn't does so extremely slow, depending on the usage or until the gradient computation starts to suffer from floating points limitations. There are options for working on these problems, and sigmoid still is very popular for classification problems. Hyperbolic tangent function is very interesting activation functions, and it's similar to sigmoid. In fact, and it's it will work quite similar in many cases. So it's not a linear function, it's well suited for combining layers. It has a range from 0, 1 to 1. That's you don't have to worry about overflow errors and so on. And what about the choice between sigmoid and tangent functions? Depending on your requirements for the gradient amplitude, hyperbolic tangent is the same as sigmoid, is subject to the gradient vanishing problem. Tangent is also very popular and is being used as an activation function in many cases. ReLU, or restricted linear unit or linear rectification unit. And this function may seem to have the disadvantages of being linear in the first quadrant. But actually, ReLU has a non-linear nature. Uh, that's it because there is a combination of two parts in this function. This in turn means that we can combine layers using this activation function. In this case, the range of the values for ReLU are between 0 and infinity. So here we have a chance of an explosion of activation due to overflow. The next point to evaluate the activation function is activation sparsity. Let's imagine a neural network with many neurons. Application with a sigmoid or hyperbolic tangent will entail analog activation of all neurons. This means that every activation must be processed to describe the network output. In other words, activation is dense and has a extremely high computation and time cost. Ideally, we would like some neurons not to fire. This would make activation more sparse and efficient. ReLU provides the opportunity to do so. Let's imagine a network with randomly initialized or normalized weights in the weight approximately all 50% of the activation are due to the characteristics of the activation function, which returns a null value for every non-negative values. In such a network, fewer neurons are activated and the network itself become lighter. So it seems that ReLU exactly what we need, but there are no limits of perfection, and ReLU isn't perfect also. There are different approaches how to improve ReLU function. Leaky ReLU, for example, is another one. And it's a compensation for a problem when we have only zero results in the first quadrant of this function. Due to the fact that part ReLU is a constant for negative values, the gradient on this part is equal to 0. Due to the 0 gradient, there will be no adjustment to the descent time weights. In this case, neurons that are in the state will not participate in the response, and they will not be responsible to changes in error data feedback and so on. And if we will use a part of negative results with a minor slope, we'll be able to battle this problem. So it will be used to turn on back some neurons in response to data we received during training. For example, it makes sense to replace the horizontal part of the function with a linear one. If the expression for the linear function is an equation for a simple equation, and we can use this technique to improve it. Another type is ELU, exponential linear unit. The main idea here is to make the gradient non-zero and gradually restore it during training. It should be noted that ReLU is much less computationally demanding than hyperbolic tangent or sigmoid, as it performs simpler mathematical operations. Therefore, when creating deep networks, it makes sense to use ReLU or its modifications. So, how do you need to decide which activation function to use? Should I use it for every case or change different in different situations? There is no clear answer to these questions. Once you know how some characteristics of the function you are trying to approximate, choose an activation function that approximates the function you are training to perform better, and it will lead to faster learning. For example, sigmoid performs well in classification tasks, since the approximation of the classification function by combination sigmoids can be done more easily than using ReLU. Use a function that will make learning and convergence faster. Moreover, you can use your own custom function. If you don't know the nature of the function you are investigating, then start with ReLU and then work backwards. In most cases, ReLU works like good approximator. Deep learning neural networks is a class of algorithms in machine learning who learn to understand data in a deeper, more abstract way. First, a little history. Many deep learning methods were known in the 80s and even earlier. For example, the first general working algorithm for deep multiplayer direct propagation perceptrons was published in a book of Soviet scientists Alexei Kirillовich Ivanenko and Valentin Grigorievich Lapa, Cybernetics Predictive Devices, back in 1965. Other deep architectures, especially those specializing in pattern recognition, have their origins in also early publications in 1980s. The backpropagation method, which is a key for deep neural networks, was first described in 1974. It was only in 1989 that uh, these algorithms were succeeded in implementing for the training deep neural networks. This solution was applied to the tasks of recognizing handwritten zip codes in post offices. For experiment, this experiment was successful, but it took 3 days to train the model, which significantly limited the application of this method. The low learning rate is due to many factors, including the problem of vanishing gradients due to the large spread of values of the trained parameters, which was analyzed in 1991. Due to these problems, neural networks gave way to support vector machines in 1990s. Deep learning gained popularity in the mid of 2000s when Everything came together. Computers became powerful enough to train large neural networks. They learned to delegate calculations to graphic processors, which speed up the learning process by an order of magnitude. Datasets became large enough to train large neural networks, and this all made sense. In most traditional machine learning methods, support vector machine, linear regression, the number of parameters is limited by the number of input features. Deep learning models are machine learning models that organize parameters into hierarchical levels. The characteristics are multiplied and added together many times, with the output of one parameter level being passed on the next level before a prediction can be made. This increased interaction between the model features and parameters increases the complexity of features that the model can learn. Parameters and linear combinations and just to remind, parameters are a set of numbers in the model that are used to calculate the model's function. You can think of this as coefficients of the function. They are turned or trained through the machine learning process to accurately transform the inputs into the desired outputs. They are simply numbers that are multiplied by added in different ways. The combination of parameters with a set of input data through multiplication and addition is known as linear combination, and this is because in cases where we have one function and one parameter, the resulting function is a line that can be extended to a higher measurement. As you remember, an artificial neural network consists of three main concepts: input layer, hidden computational layers, and output layer. More formally, in deep learning, a cascade is used. Pipeline as a sequence of transmitted stream from multiple processing layers for extracting and transforming features. Based on learning features, representation of information in data without supervised learning could be done so. Higher level functions which are in the last layers are obtained from lower level functions. This is initial layers of this architecture. Learning multi-level representations that correspond to different levels of abstraction and levels from hierarchy of presentation. Let's look at how the learning cycle works. We take the complete training dataset and split it into training, validation, and testing datasets. We let the model scan our training dataset. The model makes a prediction based on the characteristics of the sample. The calculations between possible the calculations so we take a complete training dataset and split it into training, validation, and testing dataset. We let the model scan our training dataset. The model makes a prediction based on the characteristics of the sample, and we calculate between the model's prediction and the sample label. A loss is a numeric value indicating how far the forecast is from the mark. We need to keep losses as low as possible. The model updates its parameters in such a way as to reduce the losses that will occur the next time it sees the same sample. It's called optimization stage. Periodically, for example, after we have gone through our training dataset, we may evaluate our model on the test set. In this step, we evaluate whether the parameters the model has learned how to make accurate predictions on data it has and not yet observed, in other words, on the validation set. The model doesn't learn from these examples because we didn't perform an optimization step at this stage. Without the optimization stage, the model can't update its parameters. Uh, so it's do not train here. The validation set is a test of how the model will perform in the real world. We keep a model version if it gives us the best validation performance we ever seen. The process is repeated several times and each time with different training configurations. This is called setting hyperparameters. One pass of data through the neural network, after which the weights are updated using gradient descent, is called error. Next, we'll look at the optimization stage, for which we need to understand these important aspects: loss, gradient descent, and backpropagation. Loss is a way supervised machine learning algorithms learn how close they estimated labels on the true labels of the data. The goal of training the algorithm is to approximate the function that selects it will be able to select the best model parameters. And eventually this will lead us to the best uh, loss results on all examples of datasets. There are a number of loss functions here. The choice of specific function is made depending on the number of factors and tasks that we solve. What factors should be taken into account? First, what problem we are solving? How much weight should we give to outlier labels? How balanced is our data? Equal numbers of samples in each category for classification tasks, for example. Loss functions are mathematical functions that processes all the individual losses to find the way to determine how well the model performs. In development terms, it's a piece of software code that's used to optimize a machine learning algorithm. This should be a function that will calculate how well our model is performing by comparing what the model predictions are with the actual value and compare it to the output, its output with our labels. Therefore, we need to choose a loss function that we can efficiently punish, use to punish the model while it's learning. This scenario is somehow similar to studying for exams. If someone does poorly in the exam, we can say that the loss is very high and that person will have to change a lot within himself to get a better grade next time. However, if the exam goes well, the student may behave in a similar way next time. The loss function must satisfy two criteria. The loss function should be written as the average, and the loss function should depend only on the output value. Binary loss function. It's used in binary classification. The loss function for the particular example tasks uh, could be problem here could be with such a function that it's not differentiable. That is a gradient descent method. For example, it couldn't be applied here. However, many other minimization methods will still be applicable. Simple loss function is defined as a difference between the true and predicted values. For example, it could be mean square error or something like that. One of the simplest and the most common loss functions is mean square error. So, squaring of these marks in the function allow us to make it insensitive to the signs plus or minus of the difference between the prediction and the ground truth. And also it will highlight outliers. Another one is mean absolute error. To calculate mean absolute error, you take the difference between the model's predictions and the actual data, and then take the absolute value of that difference. Finally, average the simple loss over the entire dataset. Since we do not square, we are not performing squaring, the errors will be weighted on a single linear scale. So we don't put more weights on emissions. A very common loss function is in classification problems. This function determines the loss based on the difference in probabilities of predictions. It's called cross entropy. The function is simple. You sum the negative logarithm of the model's prediction probability for the underlying true class. Since probabilities range from 0 to 1, the value of the logarithm is some negative number. So a logarithm value close to 0 is a large negative number. Since we are using a negative logarithm, the value becomes large positive number. The negative logarithm of the value close to 1 is close to 0. These dynamics correspond to what we need from the good classification loss function. To achieve low loss, the classifier will have to produce probabilities for the real ground truth class that are close to 1. Details about logarithms you can find in additional information. Let's take a look at commonly used output layers and loss functions. In machine learning tasks, regression problem is a problem where you predict a real number. Output level configuration, one node, it's a one node with a linear activation unit. Loss function, for example, mean square error. In binary classification problem, task is to classify an example as belonging to one of two classes. Or more precisely, the problem is to formulate as predicting the probability that an example belongs to the third class, for example, the class to which you assign the integer value 1, while the other class is assigned to the value 0. Output level configurations. It's one node with a sigmoid activation function. Loss function here will be cross entropy, also called logarithmic loss function. Multi-class classification problem. In this case, our task is to classify an example as belonging to one of several classes. The problem is formulated as predicting the probability that an example belongs to each class. Output level configuration. It will be one node per class using the activation function false, for example, softmax. Loss function here will be cross entropy. And let's move to the optimization in machine learning algorithms. To minimize error or loss in predictions, the model uses examples from the training set to update the parameters of the model. Error calculations are plotted as a function of weights where they are described by a loss function plot. Thus, error minimization is also often called loss function minimization. But how exactly does this work? Using optimizers, and these optimizers are used to update the weights and biases and internal parameters of the model in order to reduce their error. The most important method and bias for how we train and optimize our model is called gradient descent. The loss is calculated for the sample, gives each model parameter an idea of where to go, whether it needs to increase or decrease its value so that the model as a whole can give a better forecast next time. Each parameter of the model has a certain initial value. Often this number is set randomly. The job of the gradient descent algorithm is to first figure out how the current parameter value comprises to the parameter value that processes the optimal loss, after which it changes the value of the parameter in the desired direction. How it's being done? Imagine that you have reached some position on the loss curve and want to go down. You look where it is tilted and go. In mathematics, the analog of searching for the descent is the derivative. Taking a one-dimensional function by calculating its derivative at any point, we can determine whether the function is increasing or decreasing at that point. It turns out that our algorithm finds the slope of the function. Considering that we have a lot of signs, so-called function arguments, we can say that dimensional vector which we have will help us here. Therefore, the generalized analog of descent will be vector of partial derivatives of the function for each weight parameter. The gradient indicates the direction in which the function increases, so to find the decrease, a negative gradient is used here. After this, weight parameters are still adjusted by a certain step, which is called the learning rate. This will determine how quickly we want to move to the minimum. At the same time, we need to understand that if the learning rate parameter is too high, we can overshoot the minimum place in this space. If it's too small, we will take too long to learn. There are three ways to do gradient descent. Batch gradient descent uses all training data to update model parameters in each iteration. Mini-batch gradient descent, instead of using all data in mini-batch gradient descent, it will divide the training set into a smaller size called batch, and it's used to update the model parameters at each iteration. Stochastic gradient descent. This is a way to update parameters using only one training parameter at each iteration. This parameter is usually selected randomly. Stochastic gradient descent is often preferred for optimizing cost functions when there are hundreds of thousands of training parameters or more, since it will converge faster than batch gradient descent. Additionally, it could be noted that in reality, no one calculates gradients using such a costly method that they take derivatives for each individual element and find out how much the losses will change when moving by the infinitesimal shift along one of the coordinates. We will leave the numerical gradient method for simple cases, since otherwise these calculations for multidimensional functions will be incredibly time-consuming. To solve such problems, the so-called analytical gradient could be used. And it's also a quite old concept provided by Sir Isaac Newton and Gottfried Leibniz in differential calculus and the definition of the derivatives through a limit. It's that remarkable fact that numerical differentiation methods are based and use them, we can calculate analytical gradients with minimal uh, computation overhead. Error backpropagation. It's understandable from its name. It's backpropagation of algorithm errors as a key technique that breaks the gradient calculations into simpler gradient calculations that are combined together. This is a secret sauce that allows us to obtain gradients for large neural network models. This is a gradient calculation method that is used when updating the weights on a multilayer perceptron. The method was described in 1974, as well as its iterative gradient algorithm that's used to minimize operating error of a multilayer perceptron and obtain the desired output. At the At a high level, backpropagation allows parameters near the end of the network to send information about how to configure parameters at the beginning of the network. The process does that from the end of the network to the beginning. So it will work backward and send information from layer to layer. There are two models for implementing the backpropagation method: stochastic gradient descent and batch gradient descent. There are many options for gradient descent, and there are a number of other factors that may influence the effort to minimize gradient loss. Gradient descent isn't a panacea, and it can, for example, get stuck at local minima. Besides, could has network paralysis effects and so on. When the weights become very large values, it will stack. That will lead us to different functions which could be used here. From algorithms and functions, let's move to the simple and down-to-earth representation of unstructured data. As we remember, images are displayed as one or more grids of numbers superimposed on each other. If we are talking about gradation of gray, the smaller number is black, the larger number is white. Numbers typically range from 0 to 255, where 255 is a maximum number representing a single byte on a computer. And if we imagine overlaying numbers that represent the brightness value on each pixel on a black and white image, the result is a grid. If we are talking about a color image, instead of one grid, there are three grids for color images, each consisting of numbers representing the brightness of red, green, and blue, respectively. The magnitude of each number indicates how much color is present in a given pixel. If a certain location in the grid has high red and blue values, it will appear purple on the human eye. Words are represented using vector representation of words. The geometric spatial representation of a word has a very large dimension, and typically there are from 300 to 1024 dimensional representations of words that are being used, so that all the nuances of relationships in a large in a language can be encoded using coordinates in this space. When we move to unstructured data scenario, the number of input parameters become huge. For example, 224 by 224 pixel color image is a common machine learning example would be 150 thousands input parameters for each image. One sentence of English text consists of approximately 10 words, and standard word representation are in 1024 dimensional space. The calculation will be about 10,000 input parameters for each sentence. To train neural network models on such high-dimensional input data, we must be creative in how we design network architectures. We will begin our consideration on these network architectures For example, we need to say some words about convolutional neural networks, or CNN. They are created taking into account the specifics of image processing. They don't have a single inventor, but one of the first uses was in LeNet 5, described by Jan LeCun in 1998. A typical convolutional neural network architecture consists of the following parts. Convolutional layers, they are layers in layers for dense connectivity, fully connect layers, and this will allow us to represent each cell to contain information from the starting pixel data. And when processing these matrices, there will be huge calculational problems. Each feature can only be extracted for one or more pixel location at a time. In almost all practical situations, objects in the image are in different positions. Pixels that are located need to be on a certain side of the image, top, bottom, diagonal, and so on. Or a given pixel are strongly logically connected with each other. And reduction of an image to a feature vector destroys the spatial information that the image contains. These are the problems that are being solved with convolutional neural networks. So convolutional layer represents the main building block in convolutional neural network, and if in dense layers each neuron is connected to each neuron of the previous layer, then in convolutional neuron it's connected only to a small part of neurons of the previous layer. To reduce the dimensionality and highlight image features in convolutional layers, they are applied using a filter or kernels. The size of the region to which a neuron connects is called a filter size. In the case of one-dimensional data, such as time series, this is the length of the filter. In the case of images, this is the width and height of the our frame. The vector or matrix of parameters with which the connection fragment of input parameters is combined or a linear combination is calculated. It's called convolutional filter. The output of each linear combination is placed on a new vector or matrix accordingly to the position of the original piece of underlying data. Step by step is the distance the filter moves across the data. We can think of a filter as a kind of feature detector, since only one value is created for each fragment of the image. In the training model, we can imagine that if the fragment contains something interesting, the result of calculating the linear combination is a large number. But if the fragment doesn't contain the features of interest to us, the result of the linear combination is a smaller number. Convolutional layers can be superimposed on each other. A matrix of vectors of values created by the one convolutional layer can be considered as input to the next layer. Because each picture or value is a subsequent layer and it consists of an informational combination from a piece of the previous layer inputs. uh, Layers in convolutional neural networks can see larger and larger pieces of original input data. One number of source data positions that the current neuron can see is called its zone of spectability. Main advantages for this approach are convolutional filters efficiently scan the entire image to identify significant parameters. Parameters detection efficiency. They will store spatial information. Activations here are the result of information being detected in a certain region. Convolutional layers are what the uh, different convolutional neural networks and how they are different from each other. Convolutional neural networks are trained in the same way as dense neural networks. Also, computing the gradient for gradient descent becomes a slightly more complex procedure. CNN networks are extremely popular in medical fields such as radiology and nuclear medicine, among others. Natural language processing is a machine learning technique that allows computers to understand and organize human languages. This requires a different type of neural network architecture. The difficulty lies in the ability of neural networks to understand not the vocabulary but the meaning and context of each word. NLP takes often slightly different from the typical machine learning tasks due to the fact that the input and output data can be in the form of sequences. A sentence can be can be thought of as a sequence of words, which, as we discussed, would look like a sequence of words represented in a multidimensional space. As with images, we can consider combining time sequences data into a single vector and finding it into a dense neural network. There are a number of problems with this process. As with images, each parameter of the first layer on deep neural network will be assigned to one feature of the presented word at one time step. Sequences, especially in language, are too dynamic for this. Lack of ability to change input length is a common problem. The last layer of deep neural networks always produces a fixed size output. Currently, there are two main architectures used for NLP: recurrent neural networks and transformers. Recurrent neural networks, or RNN. They are a type of model architecture typically used in scenarios where unstructured data comes in the form of sequences. They are most often used to solve natural language processing problems. They process information one time step at a time. In language, this means processing word representations simultaneously. They can store information about past time steps in what it's called, and so it could be called context vector for text. The context vector from the previous time step is used as additional input to the current time step feature vector to provide the RNN with information about the past. The main component of the recurrent neural network is known as RNN cell. RNN cell can take as input both output from earlier layers of the neural network and an additional contextual set of values that can be used to pass information from one step to the next. RNN are used when it's important to maintain consistency. Uh, The order of incoming objects is important here. Areas of application of this class of architectures will be natural language text processing, text analytics, automatic translation, audio processing, automatic speech recognition, video processing, predicting the next frame based on the previous ones, emotion recognition, image processing, and predicting the pixels based on the environment, generating images, generating image descriptions, and so on. And talking about transformer architecture, it's next step, and it's rapidly replacing RNNs in sequence-based tasks. So RNNs were they are starting to lose efficiency if they have to deal with long-range dependencies in a given sentence. Moreover, from a technical side, it's difficult to parallelize the RNN process. One of the most powerful features of modern computing systems is parallelism. That's the ability to perform many tasks simultaneously. To process each element in a sequence, RNN needs information about past elements to make a prediction. So the calculations must occur sequentially. For long rows, this becomes a problem. Transformer architecture is built on a layer known as of inner attention. This will allow all sequences to be processed simultaneously while still producing output that's aware of the rest of the sentence. Internal attention layers calculate the contextual connection signals or weights between each element and other elements of the input sequence. An element of each position is transformed using a weighted sum of feature values from elements at other positions. Depending on the state of the contextual relationships, internal attention layers can produce multiple weighted outputs to encode different types of context. They look at the entire input sequence and then attend to the context elements differently depending on the actual values of the elements. Transformers directly solve some of the problems that exist in RNN. Internal attention layers analyze the entire input sequence at once. This allows to avoid forgetting problems related to RNN in long sequence. Because all input sequences are processed simultaneously, layers of internal attention are more significant than RNN. So this must subsequently process the input elements one by one. Transformer architectures layer multiple layers of internal attention on top of each other. So far, they have proven to be faster and more efficient than RNN architectures in many conditions. We begin our review with a public dataset that has stimulated the creation of many of the neural network architectures that are now widely used. The reference dataset is called ImageNet, and it contains a huge number of manually classified and annotated images. As of 2017, the database contained more than 14 million images divided in 21,000 categories. Most famous activity related to ImageNet is challenge, during which the best results were published. AlexNet, named after the main inventor, was introduced in 2012 and made a splash by reducing the best previous errors rate in testing images net almost double. Its architecture consists of 5 convolutional layers, between which are located pooling layers and layers of normalization. And the neural network is completed by 13 fully connected layers. AlexNet is the first architecture to use the activation function ReLU. Separate layers are used for normalization. As it turned out later, they don't provide a significant improving effect and therefore are not common in modern architectures. AlexNet was the first convolutional neural network that won the classification competition, and it is still used in some projects as a base architecture and also for training. However, since its creation, many more accurate architectures have appeared. And these architectures are VGG architecture improved the results of AlexNet more than double, from 16% of errors to 7%. It was named Visual Geometry Group at Oxford University, where it was developed. The main idea of VGG architectures is to use a large number of layers with smaller filters. There are versions of VGG 16 and 19 with 16 and 19 layers respectively. By using low-dimensional filters, we will not get many parameters, but at the same time we will be able to process them much more efficiently. Another neural network took second place in the classification during localization, and it's necessary not only to classify the object but also to enclose it in boundary boxes. The training procedures are the same as AlexNet and so on. GoogleNet is also presented on this competition. It was created by Google, and this even is an even deeper architecture of 22 layers. Google's goal was to develop a neural network with maximum computational efficiency. For this, they came up with a so-called module inception. The entire architecture consists of many such modules, following each other. In addition, at GoogleNet, non-fully connected layers are used. It contains only 5 million parameters, 12 times less than AlexNet. The module is named Inception. All the work consists of parallel application of several filters to the original image. The filter data is combined to create an output signal that is passed to the next layer. In 2015, ResNet, presented by Microsoft research team, reduced the error rate to 5.57% in the classification for images. This made it almost twice as effective as GoogleNet was. It was the first architecture to outperform a reasonably accurate human benchmark for this dataset. What happened to the neural network that we increase the number of layers? It's possible to make a conventional architecture like VDG and simply stack more and more layers on top of each other. Is it possible and will it help? It turns out that it will not help beyond a certain threshold. Increasing the network depth will worsen the results both during training and testing phases. And it's not even a matter of overtraining, since then training error would be low. ResNet produced a revolution of deep neural networks. It consisted of 152 layers, and some versions numbered more. How did this become possible? Creators for ResNet suggested that the problem is one of the optimization. Deeper models are much less tuning. Then they decided not to stack layers on top of each other to study the mapping of the desired function directly, but to use residual blocks, which are trying to fit this mapping in parallel. So ResNet became the first residual neural network. In simple words, ResNet introduced a new type of mini-model that they placed in their CNN called residual blocks. These blocks have skip connections that carry inputs or intermediate inputs to later parts of the network, allowing information from the beginning of the network to more directly reach the end of the network. As a result of experiments with ResNet, it turned out that a very deep network can indeed be trained without degradation in accuracy. The neural network achieved the smallest error in classification tasks, which surpassed even the human results. Let's look at modern image processing problems and how they compare with classification problems. An example of semantic object detection and instance segmentation is presented here. As we remember, the classification task consists of assigning one of the available labels to the image. What can be done next, especially in relation to healthcare? Semantic segmentation allows us to get pixel level detail of whether categories are presented in the image. However, the network doesn't allow us to distinguish individual instances of object categories in an image, such as individual tumors or lung nodules and so on. Object detection. In this case, the neural network outputs boundary boxes corresponding to the center, height, and width of the box that tightly borders each instance, such as an individual long node in the image. Instance segmentation. The result of the instance segmentation neural network can be a bounding box of each instance and a pixel mask corresponding to the object segmentation in each bounding box. Each of these tasks produces different types of output, hence requiring different neural network architectures or structures. Typically used for segmentation, neural networks architecture include a downsampling and upsampling circuits. The downsampling path extracts information from important parts of raw data. Path resampling generates a pixel map of the same shape and as a raw image where each pixel has a value corresponding to the segmentation prediction. Object detection neural networks predict the spatial boundary boxes of objects and have classification and regression branches. The classification branch predicts the category of objects as we saw earlier, and the regression branch outputs numeric values corresponding to the location and intents of the object's boundary box. Finally, instance sharding combines those two tasks. One branch is a classification into one category for each object or bounding box. The other is a branch of the network that creates a pixel map. This method is particularly attractive for rendering problems involving large number of duplicate or crowded objects. This semantic segmentation detection and instance segmentation tasks are more detailed than classification, and therefore they also require more detailed labels in the training dataset. For today it's all. Thank you very much for your attention.